When we introduced the topic of momentum, you heard me say that an object in motion stays in motion. That phrase is incomplete. The rest of the phrase is unless it's acted upon by an outside force. Once a force acts on an object, then its momentum changes. It will either speed up or slow down. When that happens, that's called an impulse. An impulse is simply a change in momentum. Therefore, it has the very obvious symbol of delta, which is change in p. To be complete, I should put an arrow on top of here, although if you just wrote delta p, most people would know what you're talking about. The formula, therefore, is the final amount of momentum minus the initial amount of momentum. That's how you define any sort of change. That formula by itself is kind of useless. Here I'll introduce a second formula to you, and this formula combined with the first makes for some very useful calculations. Impulse can also be calculated by taking a force, which is a push or a pull on something, and multiplying it by an amount of time. Typically, we combine these two formulas together to create the equation F delta t is equal to P final minus P initial. What this equation can do is calculate how much force is required to speed something up or to slow something down. I'd like you to notice that to change an object's momentum, you simply need to apply a force for a given amount of time. There are a couple ways you can do this. You can apply a little force for a long time, and that produces a sort of gradual change. The opposite is that you can apply a very large force for a quick, short amount of time, and that produces what I describe as a more painful change. To illustrate the difference between the different types of impulses, let's watch a short clip from one of my favorite movies, The Mighty Ducks. In this scene, pay attention to the different types of impulses that are applied to the eggs as Coach Bombay shows them how to pass.
Soft hands. You don't shoot the puck to your teammate. You sail it to him. Carp, on your feet. You send it. You don't stop the pass. You accept it. Cradle it. Again, concentration, not strength.
Like the Karate Kid, right?
Wax on, wax off.
Just shut up and try it, Averman. Such a jerk.
Send it back, Averman. Good, Averman. Charlie. Good, good. Now sail it back.
In that example, in order to catch the puck without it breaking, you needed to apply a light amount of force and kind of cradle the catch, that is, having a large amount of time. If you tried to catch the egg too quickly, you necessarily have to have a large force, which is going to cause it to break. Now for some examples. A 3,000 kilogram truck slows from 30 meters per second down to 10 meters per second in 4 seconds. We ask the following questions. What's the momentum before and after? What was the impulse that the truck received? And specifically, how much force was acted on the truck? The first question is simply a matter of mass times velocity. The momentum before is the mass of the truck, 3,000, times the velocity before we slowed down, which is 30 meters per second. That's a total of 90,000 kilogram meters per second. The momentum after is the exact same thing, only they were moving at 10 meters per second. So that multiplies to 30,000 kilogram meters per second. Impulse, remember, is the difference between the two of them, the change in momentum. So the change in momentum is after minus before. So 30,000 minus 90,000, or negative 60,000 kilogram meters per second. The final question is, what's the amount of force that was acted on the truck to produce this change in momentum? Remember that the change in momentum, or the impulse, is equal to the force that was exerted times the time that was exerted for. And so, in this particular case, we've got negative 60,000 is equal to the force, which we don't know, we're trying to find, and the amount of time it specified was 4 seconds. So, divide both sides by 4, and the force that must have been exerted on this truck is about 15,000, and the standard unit for force is newtons. If we'd like to know how many pounds that is, you could quickly divide by 5 to get an approximate answer, about 3,000 pounds. Or if we want to be a little bit more specific, 1 pound is equivalent to 4.45 newtons. And here I need my calculator. 15,000 over 4.45 is equal to 3,370 pounds. Pretty amazing the forces that can be exerted on a truck just by using the brakes and the road and the tires. Here's another example. Suppose you shoot a model rocket up, and this model rocket has an engine on the back that can provide 240 newtons, or approximately 50 pounds, worth of force. It has enough fuel to burn for 5 seconds. Our question is, how high can the rocket go? Unfortunately, we can't answer that question yet until we've studied kinematics, but we can calculate how fast the rocket can go, and I've created a program that will allow us to calculate how high that will go. The first question is, what is the impulse that was on the rocket? The impulse we can calculate 2 different ways. That's delta P, which we could find by doing P final minus P initial. That would require we know the final velocity and multiply it by the mass. Unfortunately, we weren't told that, so this particular formula won't be useful. But impulse is also defined as a force exerted on an object for a given amount of time, and we know the force and the amount of time, so this is our in. We've got 240 newtons times 5 seconds. That means it has a total change in momentum of 240 times 5, or 1,200 kilogram meters per second. Technically, that was 240 newtons times 5 seconds. So this should be 1,200 newton seconds. I'll let you in on a secret. A newton second and a kilogram meters per second are actually the same thing. When we study forces, we'll show you how a newton actually is derived from kilogram meters per second squared. So the second question is, how fast can this rocket go? That's looking ultimately for a final velocity. And so let's explore how the rest of this equation pans out. The final momentum minus the initial momentum, that's the definition of impulse, that has to equal the 1,200 we just found. The initial momentum of the rocket, as it was just sitting on the launch pad, was 0 because it wasn't moving. So this term we can actually cancel out. And so we've got the mass of the rocket times the velocity of the rocket after it's burned all the fuel. It has to equal 1,200. The mass of the rocket was 3 times v equals 1,200. So the final velocity of this rocket, after it's sped up as much as possible, must have been 400 meters per second. That's pretty fast. The speed of sound is 343. So I have a feeling that these numbers are a little bit high. Probably the thrust of 240 newtons is a little bit more than an actual rocket could provide. As I said earlier, to answer the actual question of how high the rocket can go, we need to study both forces and kinematics. Since we haven't done that yet, I've created a graph that allows us to look at that. Here's the graph, and it's set up currently for the specifics of this particular problem. Notice the mass of the rocket was 3 kilograms, the thrust is 240 newtons, and the time, that is the amount of fuel that we had, was 5 seconds. For the first part of the trip, its position increases very quickly to about 2,000 meters. At this point in time, 5 seconds into the trip, it's already 2,000 meters into the sky, or just over a mile high. Notice that after 5 seconds here, it's actually used up all its fuel. Yet if you look at the graph, it continues to rise, and in fact rises for another 8,000 meters. Why does it continue to rise? Why doesn't it just immediately fall? Well, that's the whole idea behind momentum. An object in motion continues in motion until it's acted upon by some other force. It immediately starts to be acted upon by gravity. In fact, gravity had been acting on it already. But now that there isn't a force that's continuing to push it upward, gravity has nothing to counteract it, and this object starts to slow down, and then eventually stop rising and start to fall again. However, because it had already accumulated over 400 meters per second in speed, it takes quite a while for it to slow down and then turn around and fall back down to Earth. Overall, it looks like this rocket is in the air for 90 seconds. In reality, it's probably in the air longer than that, because this graph does not take into account air friction, which would slow it down even more on its way down. And it probably has a parachute so that we can use it again.